is Shane Buchholz. I am the 2025 chair of the ASQ Chemical and Process Industrial Division. I'm very happy to introduce Ying Jin, who is a 2024 Jack Uden Prize Award winner. She is currently a Wojcicki-Troper Postdoctoral Fellow at the Harvard Data Science Initiative, and she works with professors José Zubizarreta and Marinka Zitnik at Harvard Medical School. She is an incoming assistant professor next month in statistics and data science at the Wharton School, University of Pennsylvania. She obtained her PhD in statistics from Stanford University 2024, advised by professors Emmanuel Candès and Dominik Rothenhäusler. Her research centers around statistical uncertainty quantification for black box AI models, generalizability, distributional robustness, causal inference, and their applications in biomedical discovery and human decisions. And today, she is happy to present towards optimal variance reduction in online control experiments. And feel free to ask questions throughout. I will answer them. I will look at the chat and then answer them throughout.
Great. Thank you, Shane, for the very nice introduction. And I really appreciate the opportunity to be here to talk about this work on variance reduction in online control experiments. So please do ask questions if you have any confusion about what I'm talking about, so that I do not lose you. Okay, so this is a project I did a few years ago with Dr. Shampa at LinkedIn. So it is related to the research they do at LinkedIn. Why is this a big thing for them? Because this online control experiments, or a more familiar name is A/B testing, is really getting a lot of attention in here. Like in the Stanford Business magazine, they say it's getting an upgrade in the digital age, and it's been the strategy a lot of tech companies are taking to look at the impact of their new features. So here is a cartoon that illustrates the most basic setup. So let's say you are a tech company, you have a bunch of users, you are looking at a new feature your engineering team is developing. You are not sure whether this is a good feature to deploy. So what you would do is this kind of A/B testing. So you allocate some users randomly, split them into the treated and the control team. So for the treated team, you will give them the new feature, and for the control team, they are just using status quo. And after rolling out this experiment for a while, you collect some metrics like their engagement in the posts or something like that, and compare the outcomes across the two groups. So you can think that if the differences are significantly positive, you have more confidence in the fact that this feature is really good. So this basic idea is really being used in this kind of tech companies to decide on their feature deployment. So here, you can imagine that the sooner you can get a decision, which means that your estimator is accurate, you can get your conclusion with fewer samples, the better it will be for your company. So technically, this means that the estimator of this difference in the two groups should have a smaller variance. Because with a smaller variance, we get more powerful statistical test, and you need fewer samples to reach a conclusion. And this means shorter experiment horizon for the company, so on and so forth. So the key question we are going to study in this paper, in this work, is how can we achieve the largest variance reduction possible given from our data? So we have a bunch of units rolling out the experiment. After doing the experiment, how can we make the best use of our data to get the most accurate estimator? So the largest variance reduction just means that we get the most accurate estimator with the smallest variance. Okay. So the first class of metrics we're going to look at is so-called count metrics. So these are the most standard form of metrics in this A/B testing. So a metric is just the outcome you are interested in. For example, so here the basic pipeline is as follows. We have a population of experiments. For example, this is a bunch of users you try to do the experiment on. You will randomly allocate the treatment. So here you decide whether to give the new feature to some of them or status quo to the remaining. And after some time, you measure some outcome for every unit. So in count metrics, the key feature is that the analysis and randomization units are the same. So it means that you collect outcome on a user and you also randomize the treatment, randomly give the feature on the user. So here, to give you some notations, we say giving the new feature is treatment and giving the status quo is the control. And to rigorously discuss the effect of this new feature, we have to use causal inference language. So here is just two random variables. For the treated group, we observe one random variable y of 1. And for the control group, we observe the other outcome y of 0. And we are interested in the expectation of this y1 minus the expectation of y0. So if you are from causal inference, you'll be very familiar with these notations, but no worries if not, you can just view them as two different random variables, and we only observe one of them for each unit. Okay, so as I said, the count metric randomized and analyzed the same unit. So a very simple estimator, the most basic estimator for this treatment effect, is just difference in means. So you look at the outcome for the treated units and the outcomes for the control units. You take the group-wise mean. So here, NT is just the number of users you give the new feature. The N of C is the number of users you don't give the new feature. And you take the average, you get an estimate of the effect. So the question is, can we do better than this estimator if we have more information? So that's the goal of variance reduction in this work. Of course, we're not the first person to do that. So there is a very celebrated approach called CPID in this A/B testing context for count metrics, proposed by Dunn et al. A decade ago. And also there is a very nice book from the authors of this paper on doing online control experiments. So the idea is that we can reduce the variance by pre-treatment outcomes. So it came as a very surprising and amazing result for me when I first saw this. So the idea is that apart from taking the difference in the mean outcomes, we're going to subtract the same quantity from all the units here. So for treated units, we're subtracting some beta times some xi. So the xi's are pre-treatment features of the users. For example, you have some information of the users before you do the experiment. So it can be the outcome on the day before the experiment. So we extract the same quantity from all the units in this difference in means. The idea is that it still gives us the same, it still gives us an unbiased estimator for the population quantity, which is the expectation of y1 minus the expectation of y0. That is because we randomly give the features to the people, the pre-treatment variables will have the same distribution in the two groups. So it's still unbiased. And also, as long as this xi correlates with y1 and y0, you can prove mathematically that it can reduce the variance of this estimator. So we're kind of extracting the predictable part of the outcome to get a better estimator. But I would also say there are rooms for improvement. So the first thing you will notice that we use the same beta for both groups, even if they are different outcomes. So maybe we can think about can we use different adjustments for both for each team? And also we are using a linear model, beta times xi, but maybe xi are related to the outcomes in a nonlinear way. And nowadays, because we are living in the age of machine learning and AI, we probably have a better way to look at how xi and y are related. So these are like two basic ideas we will use to improve further upon this already very good estimate. Okay. And apart from that, besides count metrics, where, let me remind you, the count metrics are where the analysis and randomization units coincide, there is a growing interest in this kind of ratio matrix in online experiment, especially in companies like LinkedIn. So the idea is that the experiment population, you can imagine the users are clustered in some way, like users belong to a company and people in the same company are associated with a company account. And because of some practical reasons, the new features have to give to all the users in each company or none of the users in each company. So you can imagine that if some people in one company receive the new feature and some people not, it will likely be a mess for that company. So in this context, people have to, like the users have to receive the treatment in the cluster. However, in the analysis stage, we're still going to collect the outcome on the level of users because users are the units who use, for example, the app and give you some information. So this is the situation where the randomization unit, which is the cluster, and the analysis unit, which is where you collect the data, the users are different. So in this case, the metrics of interest becomes something on the user level, but you are going to use this kind of average revenue per user, for example. And this poses a challenge for our analysis. So after measuring the outcome, a standard estimator for this ratio metric is we take all the outcomes for the treated units and divide it by something, some other variable for all the treated units, and similar for the control ones. So what are these y and z? Just to provide you some context. The first thing is the revenue we have touched upon. So y could be the revenue you get from a user, and z could equal to 1, which count a user. So basically, you count how many users there are in total and how much revenue in total you get from all the users. So this becomes a revenue per user. Another prominent example is the click-through rate. So it looks at how many clicks the users make for each page view. So in this case, y would be the number of clicks over all the page views, and z would be the total number of page views of a user. So here it becomes like a cluster becomes a user, and here each unit is a page view, and we got some clicks on each page view, and we are interested in this kind of ratio metric. So I'll also talk about variance reduction solutions motivated by our solution to the count metric to this ratio metric. Okay. So just to give you an overview of my talk today, I will talk about the optimal variance reduction for count metrics and followed by the optimal variance reduction for ratio metrics. There are some important issues to note in this context. And if time permits, I will talk about the empirical performance with simulations and experiments in LinkedIn. So let's start from the count metric. So before I talk about our solution, I will first discuss some insights on why we can use pretreatment variables to help our estimation. So this will help us understand the new solutions. So the idea is that here we only observe one outcome for each unit. So if both outcomes with treatment and without treatment were known, we can get an estimator with smaller variance. So if you get y1 and y0 for all the users, you can just take the difference and take the average. Of course, it's ideal, but impossible using your data, but you can try to get closer to it. So why is it better? Compared with this difference in mean estimator, we have a larger sample size. So with kind of CLT, you know that with larger sample size, you get smaller variance. And also, we have decreased single item variance, meaning that the variance of difference will be much smaller than the variance of this single outcome, especially when you expect the improvement in the treatment is very marginal. So it's great, but we cannot do that. But can we get closer to that? So the idea is that if the unobserved outcome for each unit can be predicted, then we can get an estimator with smaller variance. So technically, this means that let's get an estimator of like one estimator predicting y0 given xi, another estimator predicting y1 given xi, and we just take as if the predictors are our true outcomes, take the difference and take the mean. It is great because it's just similar to the benefit of this ideal estimator. We have made up for the unobserved outcome. We have a larger sample size and a decreased single item variance. But so a very simple idea would be we use machine learning tools to get some regressors or predictors, and we plug in to get this estimator. But it's also not, it's also too good to be true because there can be large bias. The first thing is model misspecification bias. So if we use parametric regression, it's likely that this mu1 hat uses a wrong model. And if we use non-parametric regression, like the flexible machine learning estimators, it will converge very slowly. Like the estimation error will be large, even larger than the square root n rate of the original estimator. So it's going to be even worse. And also, if you use data to estimate this mu1 hat and also plug in this to the same set of data, this will be the kind of double dipping bias, which makes the analysis very difficult. So we have these two challenges, but luckily we have this great paper, cross-fitting paper by Zubizarreta et al. So we will use the debiasing technique to eliminate the bias. So here comes our solution. The first bias, which is the estimation bias, we will use this debiasing term to adjust for it. So the first part of our estimator is we get the regressor and we plug in for the treatment effect. But we realize that there are errors in this mu1 hat and mu0 hat, so we use this big term to remove the bias. So basically, we're going to use the treated group to remove the bias in mu1 hat, using the outcome in the control group to remove the bias in mu0 hat. And again, if you are familiar with causal inference, it's just the same as the AIPW estimator, very celebrated. But here we are using it in the randomized experiment context to reduce variance. And our theory will also rely on weaker conditions. And to correct the second bias, which is double dipping bias, we'll use the technique in this Chernozyukov paper, which means that you just randomly split your data, use one fold to fit the conditional mean functions, but after you fit it, you apply the function to the second fold. So you never use the same fold to do the things, to do the model fitting and prediction. And again, we fit another group of functions on the second fold and apply this to the first fold. So it's called the cross-fitting, and we use them here. So after you getting this, you get this debiased estimator. So we have some theory showing the nice property of this estimator. The first thing is that as long as the prediction models converge to any fixed functions, we also don't need any convergence rate. As long as they converge, then we have a consistent estimator, and it's asymptotically normal to the true quantity, like the true treatment effect we are interested in, with some variance that can be consistently estimated with data. So here it shows that as long as the predictions converge, we have asymptotically normal estimator where you can do some inference. And suppose something better happens, which is that your predictions converge to the true functions. Then our estimator from the previous result is asymptotically normal, and also its variance is the smallest attainable by any regular estimator. So the regular estimator just means that anything that is asymptotically normal. Okay, so it just means that we should try best to fit the regression functions of the two outcomes. And if you are getting it correct, you get the best performance possible. So that is basically our key results for the count metrics. If you have any questions, feel free to leave it in the chat. And in the next, I will take a deeper dive comparing our estimator with some existing ones to see why it can improve. Okay, so the first thing is that let's take a closer look at the variance when mu1 hat and mu0 hat converge to anything deterministic. So if they converge, we can show that it's approximately just as if you are using this mu1 and mu0, like the limit. And then the variance would consist of two components. The first component is the so-called treatment effect variance, which is the variance of this difference in the two predictors. And the second component is the irreducible variance, which is what we cannot eliminate in the outcomes despite the best effort to fit the model. So these are like the two components, which is the irreducible variance. So we get a better variance reduction if first X is a good predictor so that this irreducible variance is smaller. And also our variance reduction will be better if the treatment effect variance is smaller, meaning that there is no treatment effect heterogeneity. So this term will be 0. And again, it will be optimal if the two quantities converge to the true conditional mean functions. So if we compare it with the very basic, the first difference in mean estimator, we can show that the variance of the difference in mean estimator can also be decomposed in a similar way, but like the first part is the same, but the second term is the same, but the first term will be the variance of this baseline predictor divided by the number of treated units, and the variance of the baseline of the predictor for the control outcome divided by the number of control units. So this is the benefit of using this plugin estimator, which is that we first increase the sample size from the number of two groups to the total number of samples. And we also have decreased the baseline variance because we have matched each pair. And in practice, this variance would be much smaller than every of them. So again, second, if we compare it with the very celebrated CPID estimator using the linear predictor. So here we are using mu1 hat and mu0 hat as the linear predictor. So essentially we are getting beta 1 xi and beta 0 xi for the two predictors. And we can decompose the variance again, something like before, and the CPID would be subtracting the same quantity from both groups. So mathematically, you can prove that this CPID estimator may not always decrease variance. So there are some corner cases if the joint distribution of x and y1, y0 is kind of weird, then in these extreme cases, the variance of this CPID estimator will be larger than the difference in mean. But our linear estimator will always decrease the variance compared with the default difference in mean estimator. It's also guaranteed to be smaller than the CPID estimator. So you can refer to our paper for proof. It's a little bit involved, so I'm not going to show it here. And yeah. And again, if we recall the most general version of our estimator, this mu1 and mu0 can be nonlinear. So we get better variance reduction if our machine learning predictor is more powerful than a linear predictor. Okay, So far, I have introduced our optimal variance reduction solution for the count matrix. We see that we can improve upon the difference in means by predicting the unknown outcome, and also use cross-fitting to reduce the bias. And this estimator also turns out to be better than the difference in mean and also the celebrated CPID estimator. And in the next part of the talk, I will discuss optimal variance reduction solutions for the ratio metrics and also some key issues to be aware of in this process, and also a computationally efficient solution with linear models. Okay, just to recap on the ratio metric, the key difference is that we are randomizing units on a cluster level. So the randomization level is a cluster, but the outcome collection level, the analysis level is smaller, it's on each unit. So the default estimator gives you a summation, it's a ratio between the summation of the outcomes divided by the summation of another random variable. And we have introduced some examples for Y and Z. Okay, so to proceed, let's make the ratio metric a little bit simpler to work with. So basically what we are doing in this setting is that we're aggregating the outcomes on the cluster level. So why do I say that? Let's begin with this definition. By decomposing the treated units into treated clusters, we're basically doing this. We're summing over the treated cluster, and within each cluster, we are summing up over units in that cluster, and divided by this same summation of Zi in this cluster, which we denote as Cj. And if we aggregate over the cluster level, this quantity is basically the total revenue in this cluster, and this is the number of users in this cluster, and similar like this. So it means that we can aggregate Y1 on the cluster level. So here, like this. So this can be viewed as IID cluster outcomes. And this is also IID cluster level outcomes. So sorry, I'm overriding the notations a bit in this slide, but you can imagine that it actually becomes the expectation of some Y1 divided by expectation of some Z1, and this becomes, so this Y becomes the aggregated cluster level outcome. This is also the aggregated cluster level version of this random variable. So for example, this is the total revenue in the cluster. This is the total number of users in the cluster, and the expectation is over the distribution of the cluster. So here a unit becomes a cluster. And we are going to change the notations from now on, just make things a little bit simple. So all the outcomes will be on the cluster level. So in this kind of ratio metric, there is a very important assumption in the literature which people have thought about, which is the stable denominator assumption. Here we call it SDA. Under this assumption, the treatment doesn't impact Z. So for example, in this company example, there is a fixed number of users in the company, so your treatment is not affecting how many users in this cluster, like either on the treatment or on the control. Your total users in the company will stay the same. In this case, there is no like two versions of the variables for this Z, so we can use Z1 equals Z0, using a simple Z to refer to both outcomes. But in another example, thinking about this click-through rate, changing a feature probably also changes the number of page views of a user. For example, using this feature, the user simply visits fewer pages. And in this case, we will need Z1 and Z0 for this denominator. And as it turns out, so previously people have thought about this assumption from a practical perspective, but here in this work, we realize that this assumption is very important for variance reduction. So just to remind you, the population quantity we want to estimate under the SDA, it will just be the difference in y1 and y0 divided by the expectation of z. And without SDA, this will be the difference of two ratios with different denominators. And as it turns out, they need different variance reduction techniques for the two quantities. Okay, so at a high level, our solution will still be we predict the unknown outcome with the bias using a similar technique. And because here we work with a ratio instead of an expectation, we will use the delta method to build confidence intervals, viewing clusters as IID units. The expression of the variance based on the delta method is too complicated. I'm not going to show them here. If you're interested, you can refer to our paper. But I'll just like illustrate a high-level idea of variance reduction here. Okay, again, we have these two different quantities with and without the SDA. We will basically do the same strategy for every quantity. So here, we use the same strategy to get this term, same strategy to get this term, same strategy for this term, and also so on and so forth, and putting them together. So let's begin with the ratio metric without SDA. Basically, we have 4 quantities to estimate. You can see that we're just basically doing the same. There are a lot of notations. You probably don't have to read all of them very carefully, but our estimator will be just this ratio minus this ratio. And at every part here, we're just plugging in the estimator and the bias with some the bias y1 in the treated company, so on and so forth. In the treated group, so on and so forth. So here, each predictor just also estimates the unknown outcome, so on and so forth. So you can see that every point converges to an expectation. And similar as before, we get valid inference if these estimators converge to any deterministic functions. And we get optimal variance reduction if they converge to the true regression functions. Okay. And for the population quantity with SDA, we also follow the similar stuff. But here, a key difference is that we're going to estimate the outcomes using both X and Z. The idea is that this Z here should not be viewed as an outcome, but a feature, because it never changes with the treatment. So to get the most out of the data, we just put X and Z together and fit a model of Y over X and Z and plug it in as usual. So actually, we are estimating the difference in means in Y as in the count metric, using X and Z as the feature, and for the denominator, we're just using the sample average of ZI. We also have a similar technical, theoretical guarantee, meaning that we have valid inference if this estimators converge to any deterministic functions, and we get optimal variance reduction for this quantity over all the regular estimators if they converge to the true regression functions. So these are like the two solutions based on different assumptions. Yeah, let me know if you have any questions about this solution. But the idea is that you can see, technically speaking, because we have different assumptions about the data distribution, we have different optimality landscape of these estimators. So to achieve the best variance reduction or the smallest variance of the estimators, we need different solutions. So in the next, so far I've talked about like you use a very general procedure to fit these two functions, but sometimes in this online platforms, it can be very difficult to use complex machine learning predictors at scale. So the linear regression solution is still the standard and also very powerful. So in the next, we're going to quickly provide a linear prediction based as variance reduction for the estimators. So again, let's start with the population quantity without SDA. Basically, we're just using a linear predictor in place of mu1 hat and mu0 hat. And you can see that you just run a few linear regressions, plug in everything, and you get this linear estimator. It's computationally convenient. Especially here, you don't need cross-fitting because the linear regression is not complex at all. It's not going to introduce this overfitting bias to you. And it is statistically robust in the sense that we can always reduce variance, even if the true regression function is nonlinear. So if the true regression function is nonlinear, but you use a linear estimator, you still get valid inference, and you get an absolutely smaller variance because the linear model can still explain away some part of the variance. And similarly, if we have this SDA assumption, we try to estimate this population quantity, then we get this linear estimator. We just look at the aggregated feature with X and Z and run a total linear regression. And we plug in these estimators for each quantity. And at the final estimator will look like this. And again, the property is conceptually similar as before. We always reduce the variance, even if the true mu1 and mu0 are not linear. Okay. So as a final note, I wanted to call for attention to this assumption in the sense that we have to be very careful about whether we trust this assumption. So we have seen that we use different solutions under the two conditions to estimate two different quantities. But what would happen if it is true or not? So if the SDA is true, we can compute either of them. It will be best if you compute, if you use our solution for this part, but it's also likely that you compute a non-SDA estimator. In this case, it's still not so bad. You can still get valid inference just because under SDA, the two population quantities are the same. You probably lose a little bit in your variance reduction because you are not aiming for the optimal solution. But based on our numerical results, especially real data, it's usually negligible. However, if the SDA is not true, but you compute the SDA-based estimator, then you will be targeting at the wrong population quantity. Like the true population quantity is this, and you are targeting at this, then you no longer get valid inference for this quantity because you're actually targeting this one. And as it turns out, you will be estimating some uninterpretable quantities. So it means that your estimator will still be like square root n around some deterministic quantity, but that quantity will be very difficult to interpret. So we think that if you are not sure about SDA, then you probably should go for this safe choice. There are, of course, settings where you should be very affirmed about SDA, such as in the company case, like under a company, the number of users is not going to be affected by your treatment. But in other cases, like click-through rate, you will probably think carefully about whether you want to make this stable denominator assumption. Okay, so far I have introduced our solutions to the count metrics and the ratio metrics with some like practical advice about the assumptions and also a computationally efficient solution based on linear model. And finally, I wanted to demonstrate some empirical performance on our simulations and LinkedIn experiments. So I still have 5 minutes, right? Okay, great. So here we conducted a bunch of simulations for the count metrics. We want to validate the performance of our method. And because we have ground truth, we can get a good evaluation. So the two question is, under nonlinearity, does the method perform better than CPID? and with linearity is the better comparable to QPID. So here I'm using a loose term, the QPID. So it is not the raw method of QPID, but the linear prediction version of our method. So I have compared it with QPID before. It's actually better than QPID. So we designed two settings. The first setting, we have treatment heterogeneity, and so the tau of x, which is, so here x is generated from normal, y is a baseline outcome plus a treatment effect. So t is the treatment. If it's under treatment, we add a tau of x to the outcome, which reflects the effect of the treatment plus some noise. So here it will be tau of x is the treatment effect component. It varies with x. The baseline outcome is somewhat linear. So we want to see if machine learning predictors can do better if we have this nonlinear relationship. In the second set of setting, we also have treatment heterogeneity, but we have a linear model. So these are just some random numbers I chose. The baseline outcome is linear. The treatment effect is also linear. So you can imagine that both outcomes are linear in the covariates. And this version of QPID, which is actually the linear version of our method, should be the best. So hopefully we're going to do as well if we use nonlinear methods, because the prediction models are just more flexible. And we do twofold crossfitting. We use random forest or gradient boosting as the estimator. So this is the result. There are a lot of numbers, but let me walk you through this. The first setting was nonlinearity. We take different dimensions, 10 and 100. So 10 means that you have 10 features of the user or 100 features of the user. We either use random forest or gradient boosting to fit mu1 hat and mu0 hat. The QPID, which is the linear version of our method, not a raw QPID. This is like the average length of the confidence interval. This is the average length of our confidence interval. This is the raw difference in mean estimator. And we look at the coverage rate. So from the coverage rate, all of the methods deliver valid inference, as our theory suggests. So it means that the random forest and gradient boosting just converges, basically. And if we look at the average length, our length is much smaller than these two methods, because shows that using this kind of flexible predictions, we are able to capture the nonlinearity and do better than these two baselines. In the second setting, we use the linear functions. Like the true functions are linear, so we expect this QPID to be the best, absolute best. Again, all of them deliver valid inference because you see this valid coverage, and our length of confidence interval or the variance of our estimator is comparable to this absolute best solution, even if we use nonlinear estimators. So it shows it's really a good option to use this kind of flexible predictors if your budget permits. And finally, I want to show the ratio metric by an experiment on the LinkedIn Learning platform. So it's probably already updated right now. It's the version at the time of paper writing, which is like two years ago. So here, basically, there is something called enterprise account at LinkedIn, which represents something like a company. And you have users associated with each enterprise, and the users can take courses on this platform, and the LinkedIn will collect some metrics like their engagement, attention, so on and so forth, to measure whether they are delivering a good product. So again, as I said, the options of features have to be assigned to an entire enterprise account, because it will be very weird if some employers in the company can receive the new feature, but some are not. And here I cannot tell you more about the feature information, but as the first set of covariates, we use the pre-treatment versions of the two outcomes. And the second set of covariates, we add some user or enterprise covariates on top of these pre-treatment versions. So the pre-treatment versions of Y and Z are the standard covariates people use in this kind of CPID or other estimators. And here is our result. If we target at the population quantity without SDA, the CPID reduces this many variance a tiny little bit. Our estimator using the same set of covariates did a little bit better, 3%, which is 1.4% improvement upon the linear version. But if we use some other user covariates to improve the estimator, we can reduce variance by much more. And second, if we target at this population quantity with SDA, that needs some careful thinking about whether it is true. But in this LinkedIn learning case, the number of users in each enterprise is likely not affected by the treatment. The CPID can already reduce a lot. By using nonlinearity, we did slightly worse. I don't know why, but using more like user and enterprise covariates, we can reduce a lot of variance compared with the default difference in mean estimator, and in the parentheses, compared with the linear CPID estimator, we can reduce 30% more variance. So that shows the power of using informative features in getting more accurate estimators in racial metrics. So with that, I think it's a good time to wrap up. So in this work, we study the optimal variance reduction solutions for both content and racial metrics, and we improve upon standard approaches by incorporating powerful machine learning predictors. And we also highlight the critical role of SDA in variance reduction for racial metrics. So if you're interested, you can look at this paper. Yeah, so that's all I have. Thank you for your attention.
All right, thank you, Yin. Thank you very much. Anyone feel free to think of some questions and go ahead and put them in the chat. Again, the slides and this recording will be available afterward. And I already put the paper in the chat here too, if you wanted to catch a look at that from Technometrics. And also, before any of you start heading out or anything, in 3 weeks we'll be having another webinar hosted by CPID, and that will be for the Wilcoxon Award winner. Let's see. So there will be an update and invitation sent out in the next week or so for that next talk. Let's see. Have you thought about, well, anyone else is thinking about any other questions? I was curious if there's any types of like doing this with multi-staged experiments, and given the results of tracking people across multiple levels of experiments and using this level of assumption.
That's a great point. I haven't seen any like methodological work doing this, but I think that's pretty relevant in practice. I think it probably depends on how you make your decisions. Like, do you mean all the users just take several experiments together, or this can switch based on previous results? If that's the second case, I think things will be pretty complicated.
Yeah.
But some ideas from this kind of selective inference might be useful. Yeah.
I was just thinking about in the the LinkedIn, the Google case, the Meta case, all these big, they'll have information about their users, but then they'll have experimental history. So I was wondering if this some
yes.
type of like analysis could be applied in stages in a way.
That's a great point. I think the choice of X can be very flexible. Any information you think can predict the outcome can be used. So if you have somewhat a related experiment or something, some related metric, even if it's not the same metric, pre-treatment, it might be used to, it might be used as the feature.
Awesome.
Yeah.
There was one question in the chat about getting RUs for this webinar. I'm not sure, but I will check it out. And then I'm gonna record your name and see if I can reach out and see. Someone had asked me for the 4-digit or so code for this, but I will check this out.
Sounds good.
All right. Well, if there are no more other questions, then we'll just leave it here. So again, thank you, Ying, and I'll stay on until we can stay on till 1 o'clock or so if there are any questions. But just wanted to let the rest of you know. Thank you for attending.
Thank you so much. Thank you so much for being here, and thank you for having me.
Thank you, Ying.